Hello, everyone. Okay, so we're continuing the lecture from Tuesday. And on Tuesday, we talked about memory allocation. So what did we say this dynamic memory allocation is? Remember, the motivation is we want to be able to create, for example, inside a function, an array, and then this array will be returned from the function, and it will not be out of scope like it happens to local variables. So we said the way we do it is uh, we use this function. I'm sorry. We use this function malloc. And malloc, what it does, it receives as an argument a number, and this number represents the number of bytes we need for our array. And what's the number of bytes? Let's say we want n ints, so we write n times size of int. So if you want, I don't know, 10 ints, for example, n will be 10, and size of int is usually 4, so this will be 40. Okay, and then we cast it into array of ints or pointer to int, and this is what our variable gets. Right. And one thing to say about about malloc. So if the allocation for some reason fails, like we're out of memory or something, then the malloc returns null. And it's very important that whatever we allocated using this dynamic allocation, using malloc, we must release at the end using the function free. So free says, this is how we use it, release this memory after you're done. Right. So let's see one example. Maybe this is the first example that we'll see. Suppose we want a function that, uh, let's say, returns 10 ints, and so an array of 10 ints, and these ints will be all the squares, 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, and so on. So, naively, we might have tried doing something like this. So we said declare an array of 10 ints, and then for each I, we declare ret in position I equals I times I, and then we return it. Why is it wrong? It's wrong because when we run this line, it will simply not work. We will return a pointer to a local variable. So once the function exits, once this function returns, the local variable disappears, so we will not be able to use it. So instead, here is what we need to do. So what we do instead is we call this malloc function, and I need to say malloc lives in this library, so we need to include stdlib. So stdlib means standard library, I suppose. Uh, and malloc, we ask for 10 ints. We cast it into a pointer to ints, or array of ints. And if everything goes well, ret should receive, a pointer to an allocated array of 10 ints. Right. Okay, so this is a standard check. So if malloc failed, we just return null. And otherwise, we populate this array with these values and we return. And it's in fact, exactly the same thing if it's not 10, but a number n. So what we will do is we'll simply ask malloc allocate an array of n ints, right? An array of size 4n many bytes, and we populate this. So what happens when we run it? So when we run main, so we declare size to be 10, we ask for an array of 10 ints. Okay, if we get null, then we write malloc failed, and we just return, otherwise we print it. Let's try to run it. So we created this file a.exe, and when we run it, yeah, this for loop prints, a in position 0 and 0, a in position 1 is 1, and then 2 squared, 3 squared, 4 squared, all the way up to 9 squared. Right. So what about this line? So what's happening in this line? So what's happening in this line is actually a memory leak. So why is it a memory leak? So look, A was pointing to a certain array. Let's try to debug it, and then we'll see what's happening. Okay. So when we run it, okay, this does the print, but is I6, 7, 8, 9. Okay, we're done. So look, here A was pointing to this array, and what's this? This is just an array of ints. When we run this line, so let's remember this number. Where should we remember this number? Maybe we'll remember it here. So 0x 7d2a8. Okay, just for a second, we'll remember it here. What happens when we run this line? This line. When we run this line, A is now pointing somewhere else. It's pointing somewhere else in the memory. It got another array and it's pointing there. So we will not be able to release this first array that we had. Okay, so that's a problem. So this means a memory leak. It's a chunk in the memory that we will never be able to release it. Well, frankly, when the function, when the program ends, everything will be released, but uh, think of a larger program that runs all the time or something like that. So we need to release it ourselves. So, if we really want A to point somewhere else, maybe one way to do it is the following. So we'll define B to be pointing to the previous A. So B points to the previous A. And now A points to a new array. And now we can release both A and B. Okay, so now both of them can be released. Okay, that's our first example. Okay, let's try another example. So another example is maybe reverse list, and it's the following. Um, so here is what we're doing. We have an integer n. We ask the user enter first the size of the array, and then we allocate n ints, and we use scanf. So remember, scanf is used to read from user input. So this corresponds to the memory of the ith int in the memory. So we're going to read this. So and after that we print it in reverse order. So this is a print I starting from n-1 up to 0. So it's going down. So it's not going up like we usually do, but this time it's going down. Hmm. Okay, so enter the size of the array. I don't know. What will be our size? Maybe 4. And now we need to enter 4 numbers. So 23, 6, I don't know, 15, and -9. Oh, and it prints the list in the reverse order. Oh, this is great. And again, don't forget to release the memory when we're done. Very important. Here is a question for you. What could this be replaced with? Okay, so maybe you pause the video for a second and think. So, okay, ARR in position I is the ith element in the array, and this is its, the memory. What could we use instead? So I'll count to 5 and I'll tell you 1, 2, 3, 4, 5. We could instead simply use this. This is exactly the same thing. So psi is the address of array in position I, same as ampersand. Okay. So, kind of while we're doing it, I'm also reminding you about this pointer. Okay. And in fact, let me just remind you in your assignment 1. So the last question, question 5, you will need to do exactly. Okay, you will also need to allocate a string inside the function using dynamic memory allocation and then return it. So here is what the function does. The function gets two strings that represent two numbers, and it must return it as another string. Sorry, and it must compute the sum and return the sum as a string. So not as a number, but as a string. And let me show you how it will be tested. Let me slightly simplify it because it's a bit complicated. Okay. So here is what our test will do. So let's say we get two numbers. One is 15, but it's not 15 as int, but it's 15 as a string. And the other one is 6. So here's what we do. We get the answer from the function, and we check that. Okay, so let's check this one. We check that the answer is indeed 21. So we do str compare, so that the answer here is equal to 21. And what is this first one? So this is the saying that ans is not null. Okay, so check that ans is not null, and the string is equal to 21, because 15 plus 6 is 21. Right. And after that, we checked, and if both checks work, then okay will be true. And then before, saying, okay, you succeeded, we have this line saying if ans is not null, right? So check that ans is not null. Because remember we said, okay, I'll say it first. We check if ans is not null, then we free, then ans was actually allocated, so we need to free. So this is what it does. We free this ans one. So how does it check that it's not null? So remember, in the lecture we said, what is being checked inside? It's being checked inside that the value of this expression, whatever is inside parentheses, is not 0. So null, if you go and look, in the actual definition, the definition of null is simply 0. Let's see, if we just check it, can we see the numerical value of it is simply 0. Okay, so this is what you'll need to do in assignment 1, and I hope I kind of parsed it for you. So okay here says, you return the string, and the string is equal to 21. So if yes, it will say okay, and if not, it will say, oh, there's an error. Okay, this is about your assignment 1. I hope it explains you what malloc is. Right. So let's emphasize it again. Inside the function, we can declare array using two ways. Either the way we did before, simply int arr115 in square brackets, or using dynamic memory allocation. ARR1 is a local variable. Namely, when we exit foo, ARR1 just disappears. Okay, it's out of scope, it doesn't work anymore. It just doesn't, it's not there anymore. ARR2 can be returned from foo and can be used outside. And we'll talk about scope of variables in a bit. Okay, let me tell you a bit more about other functions. I'll not have examples about them, but just to tell you what functions there are. So another function is realloc. So here's what realloc does. Suppose you created an array or block of memory, and this PTR is pointing to it, but then you want to increase the size, right? Maybe you first created an array of size 10, and then you say, oh, you know what, 10 is not enough, I want to make it 20. So realloc will do exactly that. So let's say PTR was 10 and you'll put 20 times int. What it will do is it will find in the memory a space for 20 ints, or for however many ints is stated here, and copy all the first 10 int or whatever was here before, it will copy to the new location. And then it will return the pointer to the new position. Okay, so realloc means, you had malloc, but then you say, oh, maybe it's not enough, I need more. It will find another position, will copy everything, and return a pointer to the new chunk of memory. It does not only expanding, it also does contracting. Namely, if you had like 20 ints, but you need only 10, you will say realloc this pointer to point to only 10 ints and not 20. So you'll put 10 times int, 10 times size of int, and it will give you a pointer to this new position. Oh yeah, and it will copy the first 10 ints. Okay, so it creates a new chunk of memory with this size. It returns it, and this part, it copies and then it deletes it. So you don't need to free the previous part, the previous pointer, because realloc will do it for you. Right. So if things go wrong, like you're out of memory, it will return null. Right. So if the array is expanded, namely this size is greater than what we had before, we copy the previous memory to the new area, in the first this many position, and the rest are undefined. And if it's contracted, it copies only the first size many bytes. Okay. And yeah, size t, so for us, it basically unsigned int. Okay, it's just a positive integer. Some more functions that are useful. So one of them is memcopy. So memcopy gets three arguments: destination, source, and num. And basically, it copies num bytes from source to destination. There is memset. So memset, what it does, it gets a pointer. It gets well, it says int, but it's really a byte. It gets 1 byte. And it says how many times you want this byte. And it sets what it does, it's in this array, or in this chunk of memory, it puts val many characters, sorry, num many characters to be val. So if, for example, uh, we call memset, I don't know, some pointer C20, we'll get basically C, 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 C. Okay, we'll get this letter C repeated 20 times. Yeah, that's what it does. And the last function I'll mention is calloc. So calloc is essentially equivalent to malloc, and then set everything to be zeros. Okay, so maybe you want your memory to start with all zeros because maybe it's convenient for you. So, right, because malloc in general does not guarantee that the block of memory that you're getting is all zeros. It's not initialized in the beginning. So calloc sets everything to zero. When you really need it to be zeros, maybe it's okay to use calloc. Oh yeah, and there is another one that's useful. It's similar to memcopy. Yeah, I think it's not a nice thing to do, right? To tell you to read it online, but specifically about this one, it's fine. So mem_move is kind of similar to memcopy, but there are small nuances. So, namely, what are the nuances? The nuances is memcopy assumes that source and destination are disjoint blocks. Mem_moves allow the blocks to be overlapping. Okay, so read about it, try it yourself. It's not very hard, but I think it's a good exercise. Okay, okay. So usually you will not need mem_move. You will need only memcopy, but sometimes mem_move is useful. Okay, right. So these functions, I'm telling you about them. I don't have examples, but when you need them, you'll just use them. Okay. Again, very important. I'll remind you again. When we are done with this piece of memory that we got, we need to release it using free. If we don't release it, the operating system will think that the memory is in use. And if we use, if we do it, yeah, if we have too many blocks of memory that are in use, in the end, we may run out of memory, although we're not really using it. And when we don't use memory and we don't free it, it's called memory leak. And we'll talk about this. Yeah, we'll talk about this next. Okay, this is what I wanted to say about memory allocation. Now to the next topic, variable length arrays. So when we did these examples, where were these examples? So when we did these examples, we said, okay, if we want to return an array of size n, yeah, we must use malloc. We cannot use, this. So let me tell you, do not use VLAs. So what are VLAs? It means variable length array. So it's basically an array whose size is a variable. So it's not a constant, it's not just 10 or 15. It's a variable that, one day may be 10, and if someone else calls it, it will be 15. And the reason is this is how the functions are implemented in C. So basically, when we create, when we declare a function, we would like to know all its local variables. So I don't know, we can have any other function. What functions do we have? I'm sure we had examples of some functions that were kind of interesting. I don't know, maybe we have something like int I, and we have char c, and so on. So we need to know all the variables because this is how the mechanism works. So it says for this function, I need this many variables, so I kind of allocate space for it in the memory. So, but with this one, we don't know how much memory to allocate when we run the program. So we'll need to do it during the running and not in compile time. While these two, we can allocate the memory in compile time, which will be a lot more efficient, right? This one we cannot. We'll do it only in runtime, right? So only after we know what's n can we allocate enough space for this AR to hold. And basically functions don't like it. So it's a super common mistake. Many compilers sort of say, yeah, it's fine. I will sort of let you do it. But sometimes, especially when n is large, all of a sudden things don't work and you don't understand why. So please don't do it. If you have a variable length array, so array whose length is a variable, please don't use it, okay? Use malloc instead. Use dynamically allocated arrays and not, and not these VLAs, variable length. All right, so let's breathe for a second and continue to the execution stack. So I will kind of explain this part. So why functions want to know all their local variables. Right. So let me tell you what's an execution stack and what's scope of variables. So an execution stack, or it's called call stack or runtime stack, it's a data structure. Okay, so it's a way to organize information that stores the information about all functions that are ever called during the execution of a program. Right? So for each functions, what kind of information do we need? So let's try to think what information do we need for each function. So there are arguments to the functions. There are local variables. There is the return value, type and value. And there is the return address, right? So when from main I call some function, when the function returns, I need to know where to go back. So when the function returns, when the function completes, we need to remember who called the function and to come back to the right position. Right? So these are this is the basic information we need to implement a function, right? So if we were to write if we were to design this programming language C or any programming language that has functions, probably for each functions, this is what we would hold. The arguments to the functions, the local variables, the return value, and the address where to go when the function exits. So let me give you an example. And the example is the following. So the function doesn't do anything interesting except that it has, sorry, the program doesn't do anything interesting except that it has three functions. So it has main, and main calls the function foo with argument 5. Foo gets this one int. It has, it does something. It calls this function bar twice, and bar also does something. Let me show you what's exactly going on inside. Okay, so let me do step by step running of this program. So first of all, we create on the execution stack a block for main. Does it have parameters? So no, it doesn't have parameters. The variables are no variables. We don't know the return value. And this is the return address. Okay, whatever this is. So, the return address will say, okay, exit the program and go back to the terminal or something. Okay. And we have this pointer that remembers what's the next line. Okay, so we start, first line is foo. So what happens when we enter inside foo? We create another block on the execution stack, okay, another frame on the execution stack, which will be for the function foo. The argument is n equals 5. What are the variables? There is n equals 5 and ret, that's for now not known. We don't know what's return value and what's the return address. So this 0 x93 whatever it is, it's basically remembers that we need to return here. We need to return to main to this foo5. So we run this, this arrow we run line by line, so we set ret equals 3. So here, ret became 3. What's happening in this line? We need to call bar. When we're calling the function bar, what happens? What will be the effect of this? The effect of this will be this. Another block is created on the stack. Right? So in this block will have, size equals 4, I equals size plus 1, so it's 5. There will be some return value, and return address will say return to this line. Okay, so we run it, and after we return, we read whatever is written here, and we return where? Here. Okay, now we're done with this line. What are we doing now? We're going to the next one. Next one says bar 8. What's the effect of bar 8? We create a block on the execution stack. Now int is 8. Okay, I becomes 9. The return value for now is not known. What's the return address? It comes back here to this line, right? To this bar 8 line. Okay, when we return, it returns here. When we get to this line, it tells us this is the return address, which corresponds to this line. So it says, oh, return here. Return 0. And when we get this return, it returns to the terminal. Okay, so I hope this step-by-step execution of this program shows what's going on inside, right? So what's going on inside is there are all these, this execution stack, and for each function we get a block on the execution stack. And when the function returns, we go one step down. When we call a new function, we call one step up and another step up. And it's like it's blocks that we can only put one on top of the other. So we cannot put anything in the middle, right? Every time we call a function, another block is added on top. When the function returns, we go one block down. Okay, I hope this is helpful. This is a super important slide, really. If you understand execution stack, you kind of understand something about how programs work. Right. So here's the thing. All local variables of a function are stored in the, in the stack frame, in the block corresponding to this function. And when the function completes, the variables go out of scope. And what happens to dynamically allocated memory? Whatever we get from malloc, they are not stored in the stack. They are stored in, I'll call it global memory for now. So when the function exits, they stay alive. Okay, so this is why we need to free them ourselves when we don't need them anymore, because this stack frame mechanism, this execution stack mechanism, doesn't take care of that. And just to say what's the terminology, the local variables are stored on the stack. This execution stack is simply called the stack, and malloc allocates the variables on the heap. Okay, so we'll remember these two terms. Stack is is the picture from before, and heap is the heap where all the malloc is allocated on the heap. Okay. And if you want to think about a stack, so stack is really a data structure. We'll get to it later, but it's like this stack of blocks. So each block corresponds to one function. The yellow one is the main, and from main we call foo, and from foo we call bar, and from bar maybe we call foo again, and maybe we call foo again. And when we go, when we're done with this function, we'll throw away the blue block and then the green block and so on until we go back to main, and then we return from main. Okay, so we add, every time we call a function, we add a block on top. Every time we return from a function, we remove the top block. Okay, so we only are allowed to add on top and are only allowed to remove from the top. Well, because with the stack of block, if you try to remove from the middle, everything will collapse and will make a lot of noise. Right, so function calls exactly the same. Each function we call adds a block on top of the stack, and when the function finishes, we remove the block from the top of the stack and continue to whatever underneath. Right, so now let's go back to variable length arrays. Why is this unsafe? Because look, each stack frame, it wants to know all its local variable in advance. It wants to know it in compile time. So when we compile the function, it will say, look, your stack frame will have exactly one int and one char. Okay, and nothing else. And when we allow these variable length arrays, it doesn't go as smoothly. So it doesn't know how much memory to allocate for each stack frame. So please don't do that. Okay, so if we don't know, so this is the rule, if we don't know the length of the array, just allocate it on the heap. All right, so that's all I have to say for this lecture. Let me just check if I have more examples. No more examples. All right, so we are done for today. Thank you all so much.